All right, here it says evaluate sine bracket a plus b. Now the formula for sine a plus b is sine a cosine b plus cosine a sine b. It becomes sine cosines, but the angles they flip. AB becomes BA. All right, so that's the formula. And that's what we're going to be using here as well. So it's straight up using that formula. But notice we don't have the cosine values. We have sine A, that's fine, that's 3 over 5. We have sine B, that is 5 over 13. But we don't have either one of these. Can we get them? What do you think? Is it possible to obtain them from what they've given us? And the answer to that is yes. Sine is so, right? Opposite over hypotenuse. So let's say this angle is A. In this triangle, what are the dimensions of this triangle? What is the opposite side? Relative to it, it's 3, right? What's the hypotenuse?
5.
5. So what's going to be the base? You have to use Pythagoras theorem.
It's 4.
It's 4. So what is cosine of A?
4 over 5.
4 over 5. There we go. So we have cosine of A. Now we're going to do the exact same thing, except we're going to do it with angle B. So if this is angle B, we know sine B is 5 over 13. What are the dimensions of this triangle? It's the same idea as before. What's the opposite?
5.
The hypotenuse is 13, the base is going to be 12. So what's cosine of B?
12 over 13.
And now we have this question in the bag. So 36 plus 20 over 65. The answer is 56 over 65, and you're done. That makes sense?
Mm-hmm.
I'll give you the formulas. There are, what, 2? Yeah, there's one for plus and one for minus for each sine, cosine, and tan. So there's going to be 6 total. Okay, we got the right numbers, but we didn't consider the angle. So let's go back here. It says it's obtuse angle. What does obtuse mean? Obtuse means more than something, less than something. So obtuse means you're in quadrant 2, basically. Yeah, we didn't consider that. The only difference that's going to make is that cosine values are going to be negative in quadrant 2. Sine is positive, but if you use the CAST rule, cosine values are negative. So this should have been negative. This should have been negative. The only difference that makes is that the answer is going to be negative, and you're done. Here, let me pull up the formulas as well. There's 6 of them. All right, so if we want to evaluate the first one there, sine x minus pi, what does it become? Which formula do we use? You can label them, I guess.
It's 4.
It's 4, right? So what does it become if you open the bracket? So it'll become sine A, so sine x, cosine pi, minus, what's the next term?
Cosine x
Yeah,
and sine pi.
sine pi, that's right, cosine x, sine pi. Now, sine pi is a 0. Sine of pi or sine of 180 is a 0. Cosine of pi or cosine of 180 is -1. So that means this entire thing is going to be 0 because sine is 0, so it disappears. And then we're multiplying sine x with -1. So the final answer is going to be negative sine x, and you're done. Okay?
Mm-hmm.
Now let's do the same thing for the next one there. Sine of x plus pi. Now the only difference between the plus and the minus is that instead of having a minus in the middle, you're going to get a plus in the middle. So it'll be the same thing. Sine x cosine pi, which we know is -1, a plus, now plus cos x sine pi, which we know is a 0. So what's the entire thing evaluate to? This is going to be 0, right? Just like before. And sine x times -1 is negative sine x. So the entire thing is simply negative sine x. For the last one, which formula do we use?
2.
2 is right. Now look at the way cosine works. It becomes cosine, cosine. Sine becomes sine cos, it alternates. But cosine stays the same. It's going to be cosine, cosine first every single time, and then sine, sine. So here this will become cosine x, cosine b, which is pi over 2, minus, now cosine, the signs are different. If it's a plus here, you get a minus here. It flips. And then minus sine x sine pi over 2. Now cosine of pi over 2 is a 0. Cosine of pi over 2 is a 0. This term. So what does the entire thing evaluate to? And sine of pi over 2 is 1. So this guy is 1. So what does the entire thing evaluate to? So we're multiplying cosine x with a 0, right? This
Mm-hmm.
entire thing becomes a 0, so you can ignore it. What's minus sine x times 1? It's just negative sine x, just like the other two. We're multiplying negative sine with a 1. That's just negative sine x, which means all three of these are the same thing. Okay, that's the question. Prove that all three of them are the same. So we're just using the formulas, which is given. And then these
Mm-hmm.
guys, you can get this from a calculator. You straight up plug, if you're in radians, just plug sine pi and it'll give you a number. So that's it for this question. These ones are gonna be, I don't know if we did this last time. Trying to think. I think we did. Let's do this one. We're not gonna do all of them, but So they've given us sine x and they have given us cosine y. Look at this, sine x is between 0 and 90 degrees. Pi over 2 means 90 degrees. Which quadrant are we in? Which quadrant is x in? If it's between 0 and 90?
The first one.
The first one. So x is this. I'm looking at sine x equals 4 over 5. What are the dimensions of this triangle? Dimension just means the side lengths. Do we know any side lengths of this triangle? And you want to look at this thing right here.
The opposite is 4.
Yeah, the opposite is 4. Hypotenuse is 5. Adjacent is going to be 3. So what is cos of x?
3 over 5.
What is tan of x?
4 over 3.
Right, and you're done with this first triangle because we're in the first quadrant. Where's y in? Which quadrant is y in? You want to look at this thing. 1, 2, 3, or 4? Three pi over 2 is 270 degrees. 2 pi is 360 degrees.
It's in the fourth one.
It's in the fourth one. So this is going to be your y. What are the dimensions of this triangle? You want to look at this thing. What is the opposite? If sine y is 12 over 13, what's the opposite?
12.
12. The hypotenuse is going to be 13. And the adjacent is 169 minus 144, 25. So it'll be 5. So that means cosine of y will be 5 over 13. What is going to be tan of y?
12 over 5.
And this is the information that we can extract from that first sentence. Now we can answer all these questions. It's not that difficult. You just use the formula. Cosine x plus y. Now if you look at the formula down there, we're going to be using 2. Cosine, it's going to become cosine x, cosine y, minus, okay, minus sine x, sine y. What is cosine x? We have it? Yes, we do. It's 3 over 5. Oh, there's a mistake here. For this one. We're in quadrant 4. Is tan positive or negative in quadrant 4?
Negative.
C-A-S-T. Only cosine is positive in quadrant 4. So tan of y should be negative 12 over 5. Doesn't apply to the x's because x is in quadrant 1. Everything is positive. And cosine is positive in quadrant 4. So tan of y should be negative. So cos x is 3 over 5. Cos y is 5 over 13. Minus sine x is 4 over 5, and sine y is, I don't know why I wrote sine y, it's negative 12 over 13. So this is 15 plus 48 over 65. So it's going to be 63 over 65 as your final answer. Does that make sense?
Mm-hmm.
Does that make sense intuitively? In the sense that we have an acute angle. 0 to 90 means it's an acute angle, and then we added a reflex angle. Let's say this is 30. Let's say this is, I don't know, like 350 or something. So the angle is 380. Which quadrant are we in? Which quadrant is 380 degrees in? remember it loops. Which quadrant is 380 in? If you know
Is it in
that.
the first one?
Yeah, it's in the first one. And does cosine being positive in the first quadrant make sense? See, this is positive when we added two acute and reflex angles. Yes, it does, because in the first quadrant, everything is positive, right? If we had gotten a negative answer here, then we would be like, okay, that should not be possible. But it being a positive answer definitely makes sense. Now the next question is cosine x minus y. The only thing that's going to change are the signs. So this is going to become minus, and this is the other one is going to become plus. So minus here means you get a plus here. The numbers are exactly the same. Cosine x is 3 over 5, cosine y is 5 over 13, plus sine x is 4 over 5, but now sine y is negative 12 over 13. So this becomes 15 minus 48 over 65. What's 15 minus 48?
Negative 33.
Negative 33 over 65. Now we had an acute angle, and then we took away a reflex angle, right? 30 minus 350 is negative 320. Which quadrant is negative 320 in?
The fourth one.
Negative 320 is in the fourth one. So when you go negative, you have to go this way, right? That's 180. That's 270. 320. Should that have been negative? X minus y, cos x, cos y. 15 minus 48 is negative 33. Something's not adding up because negative 320 degrees, right, is going to be in the first quadrant. This is negative 90. This is negative 180. This is negative 270. And if you finish that loop, it'll be negative 360. So negative 320 should have been in the first quadrant. Cos x, cos y, 15. Yeah, this is, I'm just plugging numbers in. This is not technically true because your acute angle could be 5 degrees, yeah? And your reflex angle could be 359. If this is 1 and that's 359, then you get negative 358. So it's going to change because these are arbitrary numbers. We didn't actually find the exact numbers for these two. So it checks out, but it's arbitrary. Let's try to an E. Tan x plus y. Which quadrant are we, which formula are we using for tan x plus y? We'll be using the third one down there, yeah? This one.
Mm-hmm.
So tan x plus y becomes tan x plus tan y. I don't like tans because it's fractions. And then on the bottom we have 1 minus tan x tan y, like that. So tan x is 4 over 3. Tan y is negative 12 over 5. And on the bottom we have 1 minus 4 over 3 times negative 12 over 5. How do we simplify this? Because we want a nice number. Right now we have a not so good looking fraction. What do we do in the numerator? So the common denominator between 3 and 5, yeah, is what?
15.
15. So you multiply this by 5, multiply this by 5, multiply this by 3, multiply this by 3. So you'll get 20 minus 36 over 15 in the top quadrant. Oh, sorry, in the numerator. And on the bottom, -4 times -12 is +48 over 15. So this one has an invisible denominator of 1. So multiply this by 15 and multiply this by 15. So 15 plus 48 is 63. So you get 63 over 15 on the bottom. This 15 and this 15 cancels out. So your final answer is going to be -16 over 63. And you are done. Okay? And we end up in the fourth quadrant, and tan is expected to be negative in the fourth quadrant. And we are done. I'll do a quick exercise with you. So let's talk about this. How do you think a population grows? What function does it look like? The growth of a population. It looks like this. What function does this represent? Is it x squared?
No.
Then what is it?
Is it exponential?
It is exponential. I'm trying to find a formula. So it's definitely exponential, okay? But now you have to think about this in terms of practicality. Can a population grow exponentially forever? Or is it going to hit some type of a blockade? What do you think?
Eventually it will.
Eventually it will, right? So yeah, population do grow exponentially, but what ends up happening is it's limited by something called the k value. And k is the carrying capacity. It's basically the amount of resources available in the environment. For humans, we have a lot of resources. So for us, up until right now, if we're looking at the entire population, our growth will look just like this, okay?
Mm-hmm.
It will look exactly like this. But let's say you're looking at a species, and by the way, here, this on the x-axis, you have time, on the x-axis, you have the population. So time being negative is redundant, so you can ignore that axis. You can just look at it in this axis. But let's say you're looking at some other population. Let's say you're looking at the population of squirrels in the winter. Is there unlimited food for squirrels in the winter time?
No.
So are they gonna grow forever? No, they're not, right? They are not going to be growing perpetually. So what does their thing look like? Turns out it'll look like this, okay, in the beginning, yeah?
Mm-hmm.
Here's the k value. This is the resources. The population cannot exceed beyond the available resources. So it'll look like this. And that right there is a horizontal asymptote. This thing is a horizontal asymptote. And this thing, so this is an exponential growth model, applies to humans. But for almost any species, we have a k value as well. We just haven't hit it yet. But for other species on the planet, most of them have already hit this. This is called a logistic growth model. Kind of makes sense? Now, why is this important? Where am I going with this? I'm trying to find an equation. but it is not letting me. Just give me a second. Because this one is basically gonna be e to the power of rx, where e to the power of x is your thingamajig. What is it? It is your growth model. So in this case, we know it's going to be a exponential growth model, yeah? And r there represents the growth rate, the population growth rate. But for logistic growth, it's actually a bit more trickier. And we're going to do some algebra on this. So the exact formula, it's going to be different depending on the book you use, but for the most part, this is the formula. NT is a population at time t, okay? That is going to be equals to K, which is the carrying capacity, divided by 1 plus K minus N0, which is the initial population, divided by N0. And this will be times e to the negative RT. So there's a lot of things going on here. R is the rate of increase. T is the time. Time can be like 1 year, 2 year, 3 year, 4 years. N0 is the initial population. And T is the population at time T. So let's say at time 20 was a population. So that's going to be NT. And K is a carrying capacity, which means like, let's say K can be anything. For humans, it's about, I think we've already surpassed it actually in term, but we do have a lot of resources. Yeah, I don't know if we have surpassed it for humans. We're headed towards what, 9 billion? I think we can do 9 billion. I think it's about 12 billion is the carrying capacity for humans before we have to fight for resources. So this is the model. It's way more complicated than your normal exponential growth model. Now, why are we talking about this? I want us to come up, okay, from this formula that they've given us, I want us to solve for R. And it's a pure mathematical question here, this one. We need to isolate for R, okay? R is over here downstairs in the denominator. And it's tucked in the exponent of the denominator. So it's definitely tricky, but we can solve for R. How do you think we do this? What would be the first step if you're trying to solve for R? If your unknown is in the denominator, what do we do?
You multiply it.
You multiply. So what I'm going to do is I'm going to multiply both sides by this entire thing, okay? See this?
Mm-hmm.
And then at the same time, I'm going to divide both sides by NT. So what's going to happen is that they're going to switch positions. So 1 plus K minus N0 divided by N0 is going to come here on this side. You have e to the negative RT, and that is going to be equals to K over NT. Now what do? We're trying to solve for the R. We need to get rid of everything that's not R from the left-hand side of this equation. What do you think? Would you divide by this term or would you subtract 1?
Subtract 1.
Subtract 1 is right. So that 1 is going to come over here. Now what? What's the next step? We're trying to solve for R. We need to get rid of everything that's not an R. So we need to get rid of this term. We need to get this T. We need to get rid of that E as well. Which one do we get rid of first?
The stuff in the bracket.
Yeah, so we're going to divide both sides by that. So it becomes e to the negative RT is equals to K. You can take a common denominator here. This is going to become k minus nt over nt, right? And I'm going to divide by this, k minus n0 over n0. And remember, if you're dividing, you can turn that into a multiplication sign if you flip it. So this is going to become times n0 over k minus n0. Now what? We're only a few steps away. We need to get rid of e. Don't know if you remember this. How do you get rid of an e? Or we have our unknown in the exponent. What do we do if our unknown is in the exponent?
You use log?
Yeah, you're going to use logs. But when you're talking about e is the natural number 2.7, whatever. Instead of using logs, you use something called the natural log, ln, natural log. This you'll use when you're dealing with e. So we're going to take the natural log or ln on both sides. Why do we do this? It's because the ln and the e, they cancel each other out, which allows this exponent to drop down on the base level. So this becomes negative RT is equals to ln of that entire thing, k minus nt over nt times n0 over k minus n0, like that.
Mm-hmm.
Now we need to get rid of this negative t. What do we do? We're trying to solve for r, so we need to get rid of that minus sign and the t.
You divide by negative t?
Yeah, you divide by negative t. So this becomes everything divided by negative t, or the negative sign can come in the very beginning as well. There we go. That's the formula for r. Kind of complicated. This thing is called logistic growth, okay? This is gonna be a real life model, basically, a practical model. So what actually happens is that there is a hard limit. There's a hard limit of the amount of resources that's available. Initially, it's gonna be an exponential model. It's gonna grow very fast. But as you approach this limiting resources, or that limiting curve, in chemistry, it's called a limiting reagent. When you're doing like reactions and whatnot, it's gonna skew and it's gonna write the asymptote like this. And it's gonna follow this k forever. This is the best case scenario. What usually happens though, it doesn't have to be like that. Especially for like in the animal kingdom. What happens is even though there's a hard limit k, the population is gonna exceed it. What do you think happens if the population exceeds the amount of resources that's available?
The population starts to decrease?
So it can either decrease like this, which is the best case scenario, right? Like that. It'll come down until it's under the K curve again. This is the best case because you've lost this many people now. You see this entire chunk, they've died. They're gone. So this is a second base case scenario where it's gonna come down and then it's gonna write the asymptote. And now here's the worst case scenario. It's gonna go boom all the way up, yeah? And then it's gonna bust. Sharp decline. Have you heard about a species going extinct?
Mm-hmm.
There you go. Once you exceed your carrying capacity, you can either stabilize, easier said than done, or the entire population crashes completely. And now the species has gone extinct. Okay?
Mm-hmm.
You'll talk about this in science if you do like biology. I know grade 10 they teach you microbiology, which means like you look at cells and mitochondria and this and that. But if you ever do macrobiology, now macro means at the bigger scale, then you're gonna talk about things like this. It's pretty interesting. We're definitely
Mhm.
headed towards, I think we're gonna stabilize, right? Because we're pretty smart and we have like laws and whatever. This is probably what's gonna happen with humans, but who knows, right? This could happen for war. Due to war, this could happen. And it has happened in the past. It hasn't completely gone extinct, but like it's come over here, okay? And then it slowly starts stabilizing again until the next event or the next bust or boom. But look at this. Look at the math behind it. It's pretty nice. Everything kind of checks out. It makes sense with logic. Now, how in the world did they derive this? I do not know, but someone or some people were able to come up with this. Before this, we thought it was an exponential model, which would have been so much easier. It would have just been like e to the power of RT, and then you had your initial population. This is the exponential model. But it's not practical because we didn't consider K. When you start considering K, then this is what you come out with. Okay, let's do a quick question here. Let's say your rate is 5%, okay? Let's say your carrying capacity is 50,000. Let's say this is the number of turtles in the sea or something like that. And let's say your initial population is 10,000. The question is, 20 years later, what's the new population? So that's the question. And now let's see if it's sustainable or not. So I'm just going to plug everything into this formula. 50,000 is our K value. This is the maximum number of people it can support. 1 is just a 1. And then you have 50,000 minus 10,000 divided by 10,000. And then you have E is just a constant to the negative. What 5% in decimals? 0.05. 0.05 and the T is 20. Let's plug this in and we can make predictions about where this population is headed. 40,000 or divided by 10,000 is 4 times E to the negative 0.05 times 20, and then 50,000 divided by this. So the population after 20 years, according to these values, yeah, it's going to be 20,230. Is that sustainable? If the carrying capacity is 50,000, your population is 20,000. Any issues with that? No, no issues with that. We're over here. Actually, we're not, we're less than halfway. So if that's 50,000, like we're somewhere over here, completely fine. This population is going to continue to increase exponentially. Okay. Let's say, what about 100 years though, or like 200 years? Let's see what happens then. So it's going to become 1 plus 4 times e to the negative 200 times 0.05 and 50,000 divided by 50,000. Even after 200 years, you're almost fine because you're going to get 4990. This is what the model predicts, okay? So after 200 years, you're going to be right on the cusp. When you're using this formula, actually, your maximum value is always going to be less than 50,000. So this is the predicted model, or the predicted value. In reality, it's not quite possible to count every single fish or whatever you're trying to monitor. So if it goes beyond this, let's say it goes beyond 51,000, then either it's gonna stabilize or it's gonna bust, okay? Population growth models. Is that interesting? Or no?
Sort of.
Is this the best thing you've done in science thus far? Definitely,
Um,
definitely not, probably. This is more biology, right? It's not chemistry, but I'm sure you can apply this to chemistry. You can look at, I don't know, like the pH levels of the soil or of the ocean. Do you know what the pH of the ocean is? You know what pH is?
mm-hmm.
What is it? What's pH?
It's like the amount of like acid or base in something.
Yeah, it's the measure of acidity. So if you're 7, it's neutral, like water. More than 7, it's basic, like soap. And if you're less than 7, like, I don't know, like vinegar or something, then it's acidic. What do you think the pH of the ocean is? Is it neutral, acidic, or basic? What would you expect it to be?
Um, Close to neutral.
Close to neutral? So like 6.9 to 7.1-ish? Somewhere there?
Maybe.
Right now, the pH of the ocean is 8.1. It's actually pretty basic. 100 years ago, the pH was 8.2. So the pH has gone down, right? What does that mean? What's happening to the oceans? It's getting more acidic or more basic?
More acidic.
More acidic. Is that a good thing or a bad thing for aquatic ecosystems?
I assume it's bad.
It's bad, right? Yeah, it's definitely bad. This is called ocean acidification. It's definitely not good. Acidic is bad. What do you think is causing this?
Isn't it like carbon dioxide or something?
It is, it is. Basically, when your greenhouse gases interact with water in the atmosphere, it turns it into an acid. H2CO3 or H2CO3. You know what this compound is? This is in drinks such as Coke. It's a thing that makes it like fizz up. What is that thing called? It's carbonic acid, okay? So when your carbon dioxide in the atmosphere, when this, and by the way, the concentration of this has been going up significantly, interacts with rain or water particles in the atmosphere, it is going to end up producing carbonic acid. And where do most of our water end up? Ends up in the ocean, right?
Mhm.
That's why. That's why this is happening. Is it a good thing? Definitely not. There's a lot of bad things happening in the ocean, and this is one of them. Another critical one is obviously plastic, right? You've seen like videos with like turtles having like plastic stuck in them, or
Yeah.
whales dying because of consuming plastic. There's a lot of things happening in the world, but anyways, yeah, this is chemistry right here. So pH allows us to see what's actually happening. And this may not seem like a big deal. It's a huge deal. Ocean is super big. So the fact that it's dropped by 0.1 So we're probably dropping by like 0.2 by 2050 or something like that. It's getting more and more acidic, and it's not good for anything. Here's why sine, cosine is important. Think about the waves of the ocean. Do they have patterns? How would you describe
Mm-hmm.
the waves or the tides or whatever? It is periodic, right?
Mm-hmm.
This is gonna hit the beach, and then after a certain time, this is gonna hit the beach, and after a certain time, this is gonna hit the beach. It is periodic. And which functions are periodic? Well, sine and cosine. Sine looks like this. It's very different from x squared or x or something like that. These guys are one and done. But sine and
Mm-hmm.
cosine, they go forever in both directions. So that's why it's important to study them, so we can model real life scenarios. With compound angle formulas, let's look at some double angle formulas. And these are all the formulas. It doesn't get more than this. Let's say I want to find sine of, I don't know, something nice. Let's say I want to find sine of 120. I can find this using the cast rule, okay? Or I can look at it this way. Sine of 120. Last time we looked at this, we did sine of 60 plus 60. That's a compound angle formula. If you're adding two angles to make your principal angle, then that's a compound angle approach. But instead of adding, if you want to multiply it with 2, 120 is 2 times 60 degrees. This is called a double angle approach. Now look at the formula for sine of 2 times an angle. So it becomes the 2 inside comes outside of sine, so it becomes 2. And then now our theta is 60 degrees, so it becomes 2 sine 60 cosine 60, yeah? And we can get this from our special triangles, 31, 2, root 3. So sine 60 is opposite, so root 3 over 2. What's cosine 60?
1/2.
1 over 2. So this 2 cancels out one of these. So the answer for sine 120 is root 3 over 2. Okay? So that's how you can use a double angle formula to get the same answer. It's just about knowing which one to use when. Like let's look at a question here. And sometimes you have to work backwards. In this question, they've already expanded it for us. We have to work backwards. This is, by the way, what is this? 22.5 degrees. So it wants us to find the value of 2 sine 22.5 cosine 22.5. Those values do not exist. Well, they do exist, but it's not going to be an exact number. The only exact values you can get is 30, 60, and 45, and then the variations of those across all 4 quadrants. So we're over here, okay? Remember, this is 22.5. Both of them, 22.5. If I want to work backwards, what does it become? Using that first formula up there. It'll become sine of 2 times 22.5, right?
Mm-hmm.
Or pi over 8. 2 times 22.5 is 45, or pi over 4. And we know the value of pi over 4 is from this triangle, 1, 1, root 2, pi over 4, pi over 4. It's 1 over root 2. And that's it. Pi over 6. We do know what pi over 6 is. Pi over 6 is 30 degrees. But let's make our life easier. What is this going to become? If you use this tan formula at the bottom, okay? This is 30 degrees. Pi over 6 is 30 degrees. What do I get? We're over here. We're trying to get over here. It'll be tan of what? Notice the angle doubles, okay? If you're working backwards, if you're going from here to here, the angle doubles. So we started out with 30, now it's going to become 2 times 30. It'll become 60, okay? It'll become 2 times 30 or 2 times pi over 6, which is pi over 3. It's 60 degree. Yeah, it's 60. And tan of 60 is root 3. Cool.
Mm-hmm.
So these are the double angle formulas. Let's try this one. Cosine is negative. Which quadrant is cosine negative in? Cosine is negative. Which quadrants is cosine negative in? There's 2 of them. C-A-S-T, right? Over here and here. Quadrant 2 and quadrant 3. Cosine is adjacent. So this is going to be adjacent over the hypotenuse. So in those 2 quadrants, this is going to be our theta. The adjacent is going to be 2. The hypotenuse is going to be 3. What's the opposite side? Use Pythagoras.
It's going to be the square root of 5.
That's right, it's going to be the square root of 5. Same thing down here because cosine is negative in quadrant 3 as well, so we could definitely be down here. So the hypotenuse was 3, and it's going to be root 5. All right. So let's say we are in quadrant 2. What's the value of sine theta? Look at that triangle. It'll be root 5 divided by 3, yeah?
Mm-hmm.
What about in quadrant 3? What's the value of sine theta? Opposite over hypotenuse. It'll be the same
It's
thing.
also 5 over 3.
But is it positive or negative in quadrant 3? Sine. Sine is
Negative.
positive in 2 and 1. Yeah, it's going to be positive. Now, let's look at that. Now we can do the questions. It says find the value of cosine 2 theta. You have 2 different formulas. I'm going to use the one on the top. So that is cosine squared. So negative 2 over 3 cosine. You square this, and you take away sine theta squared. So sine theta is 5 over 3 squared. So this will be 4 over 9 minus 5 over 9. It'll be negative 1 over 9. That's the value of cosine theta, 2 theta, sorry. And for sine 2 theta, you got to use this formula. Sine 2 theta will be 2 times sine theta times cosine theta, like that. This is in quadrant 2. So it'll be negative 4 root 5 over 9. These are the final answers in quadrant 2. And then you do the same thing for quadrant 3. In quadrant 3, cosine is still negative, so this will be the answer for quadrant 3 as well. And you're squaring them anyway, so it doesn't matter. But for sine 2 theta, both of them are going to be negative. This 5 over 3 is going to be negative. So your final answer will be positive. The numbers are going to be the same, but it'll be positive 4 root 5 over 9. And you are done. Okay.
Mm-hmm.
All right, let's call it a day there.
Okay, thank you.
See ya.